So I'd like to say something about the Forerunner projects. A few people are going to present on these, but there are 5. I should say that most of the research funding in this hub is actually going to be distributed through grants, but we have, and we'll talk about that in a minute, but we have 5 day 1 projects which are listed here across the core partners and across areas: materials, chemistry, synthesis, AI, of course. Just to say, sort of more generally, obviously we have teams in these projects already, but they're all open for collaboration. So we're keen to bring new people in and expand these projects, and maybe some of the funding call proposals will build around these core Forerunner projects. So we'll go through each in turn briefly. I'll talk about the first one. So this is Human in the Loop, and this is led by Liverpool, but also involving other partners. And actually, it's 2 sub-projects. One is based around closed-loop robotic experimentation. That's led by me. And the other one is based around in silico crystal structure prediction for inorganic materials. That's led by my colleague, Professor Matt Rosinski. But they're both unified by the idea of finding better ways to inject human knowledge into these approaches, closed-loop robotics and crystal structure prediction, and how to fold in human knowledge into these AI-led or computational robotic-led workflows. So we'd be interested in talking to people in various areas here, could be natural language processing and other areas. Next project, we'll hand over to Graham Day.
Hi, I'm Graham Day. This is Forerunner Project 2, which is currently led in Southampton, looking at large-scale crystal structure prediction. So this project addresses data availability for the community, focusing on the area of molecular crystal structures. What we're doing is trying to automate pipelines for scaling up this type of simulation. Crystal structure prediction involves predicting all of the stable crystal structures for a given molecule, and eventually coupling this with property predictions. So the idea of this project is to create a step change in the amount of data available in this area for training of machine learning and AI methods, for example, energy predictions, property predictions, and inverse design generative methods. We've made a good start already on the project, generating crystal structure prediction landscapes for beyond 1,000 organic molecules. You can see a couple of publications in the bottom right and diagrams of some of the molecules we've looked at. So this involves already over 4 million unique crystal structures and their calculated relative stabilities. And we've also started to test how these methods might be used, for example, in training machine learned force field methods.
Hi, my name is Jackie Cole, and I'm leading the Forerunner 3 project, and that is on data-driven materials discovery. And the approach being taken here is essentially a design-to-device approach, a pipeline, as you can see, is shown in the slide. And what I have background in doing is essentially mining data from the literature, which essentially forms a custom materials database for your needs. Particularly, my group develop and maintain the chemistry-aware natural language processing tool called Chem Data Extractor. So it's an open source tool. It mines the scientific literature, particularly pulling out material property information, and then automatically compiles it into a database, that's geared towards your application of your needs. So having mined the right data for your problem at hand, which, the area of, say, materials that you want to discover a new material in for a given application, we then look through the data in various ways, either a question and answering way or a machine learning approach to predict new materials from that historical set of data coming from the literature. And then we validate experimentally those predictions. And I think there's a real opportunity with the AIchemy link up to not just do what we've done before in these sort of pipelines with experimental validation, just look at the lead candidates and see if if they actually we can synthesize them and put them into a device and check they work, but actually use the high throughput facilities that you've just seen and with the robotics link up. So that's never been done as a full pipeline. You know, with our sort of side coming from the data mining side and then the experimental validation from a high throughput and together as a full load. So that's potentially, I think, an opportunity for this Forerunner project. Thank you.
So Forerunner 4 is focused on generative AI for small molecules and materials, and we'll look at creating a foundational generative model covering multimodal chemistry data. So that includes molecular and crystal databases, experimental spectra, as well as computer properties coming from calculations. And we'll also allow the transfer from one piece of data to another. And then again, this will link up directly to experiments. One thing I didn't mention when I talked about facilities is that we will be buying a small amount of additional low-cost equipment, both here and at the University of Liverpool, and that's being led at an Imperial side by Becky Greenaway, and this will allow sort of flexible setups for different automation workflows, and people will be able to do secondments if they want to come and test out their own workflows in this area. But this will also be used for supporting these Forerunner projects. And then finally, for Forerunner 5, this will be led by Ruth Meisner and also many others. We'll focus on identifying and optimizing reaction mechanisms with multi-fidelity AI. Yeah, there's a lot of experience, for instance, in Ruth in conservational optimization here, but also with the automated platforms for exploring reaction data. So we'll look at building multi-fidelity machine learning models that combine both computational data, for instance, from DFT and machine learning force fields, but also experimental data, for instance, spectroscopic data coming from online analysis, for instance, IR, mass spec, and NMR. And so we'll have an active learning approach that automates both the computational and the analysis coming from the characterization facilities in the lab.